with Stephen and David Chisnell, although I'm now working at ARM and they've paid for me to come here, so I am very grateful for that. Okay. Also, this has gone slightly flickery, but we'll see how it goes. Okay, so very briefly, what I'm going to talk about, what is LiveCrunch and why should you care? Some things that it does in order to work. Stephen's going to come up and talk about the runtime and some other stuff that he's responsible for. And yeah, that's it. Okay, so the talk is runtime type checking in C. But C is statically typed, right? Sort of. Here's a pointer cast. So we're trying to convert some other pointer to a bar, right? So sometimes this might be correct. If we're lucky, it is. But sometimes it might be wrong. And this could be bad in a number of ways. So if you're lucky, this is really annoying. I do apologize. If you're lucky, bar and some other pointer point to things of completely different sizes. And when you try and set X, it will segfault straight away, and you'll realize that there's a bug. If you're really unlucky, then they are the same size, but can mean completely different things, at which point your program will continue for maybe who knows how long until, many function calls later, you end up with a completely corrupted data structure, or you try and dereference 3 or similar. It's bad. Okay. So, yeah. So here are some tools that I could think of that you might try to catch this kind of bug. So memory sanitizer, not really, because that's an uninitialized memory, which isn't the problem. Address sanitizer gets closer. So if you hit the 2 different structs but different sizes case, then address sanitizer might catch it, because that's an out of bounds error. And then some other ones, thread sanitizer, undefined behavior, they're not really the problem. Compiler warnings won't help you here because you've quashed them all by doing a pointer cast. Maybe in a few cases it might tell you. Val grind is similar to address sanitizer and what it will catch. Okay, so what is LiveCrunch? So it's a framework for keeping track of the types of all your memory allocations and statically allocated stuff as well, I think, at runtime. So any point in your program, you can call into the runtime library and say, what type is this pointer? And it will say, it's a int or a foo or whatever. So here's an example. When it comes back, Clang CC, you build your program with that, which is a compiler wrapper around Clang. So it uses a Clang sanitizer and then to instrument your code and then does a bunch of other stuff. And then run it with a preloaded runtime library, and then it will come out with this error message, which in this case is from one of the test cases, and it's saying you tried to cast a thing to a stat, but it's actually a sock addr. And then hopefully that will tell you where your bug is and save you hours of debugging time. Cool. So how does it work? So there's several things that it does in order to give you these messages. So the first thing is you have to go and modify all the pointer casts to actually check them. So here's a kind of pseudo C representation of the transformation that it does. This isn't actually what happens. This is just the effect, which is that you call that is a U function with your pointer and a reference to a structure representing the type that you think it is. And then it prints out a warning, and then does the cast. Oh yeah, one neat thing about this that I didn't mention earlier is that you only have to check the cast. You don't check the uses of everything in the cast, which means you might instrument fewer things than other tools like this. Okay, the next thing, you actually have to find out what types everything is. So this finds the compile times types and then uses that at runtime. So it just finds all your allocations and then spits them out into a file with the type that it thinks it is, and the compiler wrapper will use that later. And then I've put linker magic. Stephen's going to talk about that in a bit. Maybe it's not that magic. And there's a runtime library as well, which actually looks after the types when you're running your program. Okay, so this is a picture of the previous slide because everyone likes pictures. So again, take your C source code, compiler wrapper, that will run Clang, which does all the interesting program transformations. Well, Clang's code gen, and there's an LLVM pass which does the more interesting stuff as well. So flickery. Yeah, and then there's a little bit extra in the compiler wrapper. And then eventually you run your program and get a warning and are happy that you found a bug. Cool, okay, so this is an actual instrumented pointer cast. It's not actually the C to C transformation that I showed earlier. It's in Clang's code gen. So you generate some call to the checking function. There's some branching that I've omitted so it would fit on the slide that will print out a warning if it fails, and then you actually do the cast. That's not wildly exciting. This is where it gets more interesting. So the important part of this is finding out what the type of every allocation actually is. Yeah, so here's an example of an allocation. So you'd think it should be quite easy to find the type, because on this statement it's mentioned 3 times what type it is. But, there's always a but. Okay, no, there's no but. Let's try this. So let's try using the type that you've assigned it to first. Or in this case, that's equivalent to saying the thing that you cast it to first when you execute your program. Because even if you omit that second cast, I think Clang gives you an implicit cast in the AST. So that might work, but what about this? So it looks kind of right at a glance, but we've only allocated enough size for a pointer to a foo and not for an actual foo. And this is the exact bug that LiveCrunch is supposed to catch. So yeah, let's try a different way. Okay, so let's try looking at the size. So the size of the allocation, again, you know, you've got your AST and Clang, and you can say, here's a malloc call. The argument's the size of. It must be a foo, right? So it's kind of reasonable, but it's not something that you want to implement as a Clang AST thing, because as soon as you get anything remotely complicated, you end up trying to do a data flow analysis on an abstract syntax tree, which would be painful. So what we actually do is do it in an LLVM transform. It's kind of more of an analysis, but you have to remove some metadata, so it's a transform. So you generate a function call because, so by default, I think Clang will just give you the number in the IR, so size of int gives you 4, which doesn't tell you much. So you have to put a pretend function call that tells you what the type actually was. So we do that, and then we basically find all the allocation functions. So you just go through malloc, calloc, anything else that sounds like alloc, rhymes with alloc, and then follow the use def chain, or def use, I forget which way around it is, until you find some size of expressions, well, your dummy function call, and then do the maths and find out the type. Okay, so I said do the math. Oh yeah, and then you remove the function calls. So I was talking about doing the maths to find out the type, because there's all these allocation idioms that you have to work around. So we've got things like arrays of lots of items. That's pretty simple. The second one is where you might have a structure followed by a variable length buffer of maybe some other type, or just char or void or whatever. And then idioms like the last one, which is the length of a constant array. You might allocate n elements of some other type. So we can support all those. It uses a technique, it's a bit like dimensional analysis, but it's a little bit easier because there's only a fixed number of these things, and because it's types, it's not real maths, unless you like semantics. Anyway, yeah, so cool. Stephen.
All right, hi everyone. Can you hear me? Yes, sounds like you can. Great. So, as Chris said, there's a runtime underneath all this, and the job of the runtime is to keep track of, for every allocation in your program, keep track of what type of data is stored there. And what's going on at runtime is that the runtime is actually tracking a tree of allocators, the tree of allocators that are responsible for managing memory in your process. So at the top level of the tree, you have the operating system mechanisms that give you memory. So you have the mmap, and you have your program break. You also have the stack, which I've not shown on here, but that also counts as an allocator. And then underneath that, you typically have a bunch of other things like your libc malloc. You might have another malloc in some other part of your program. You might have a VM that's got some garbage collected heaps. All of these are allocators, and we're actually observing allocations. The LiveCrunch runtime is observing allocations as they happen, and it's maintaining any extra metadata that we need so that we can have type information for all of these different kinds of allocation. So what is this type information? What does it look like? Well, we actually generate, most of this stuff comes from dwarf debugging information. So in the compiler wrapper, we make sure that you're turning on dwarf, and then we post-process that dwarf into an efficient runtime representation. So every data type in your program is reified. It's made into an object at runtime. And here's an example where we have an ellipse data type. And because it's ellipse, but it contains doubles, also has this nested struct. So actually, we're going to generate a bunch of different data types that are all going to be referring in between one another. So you can see we've generated an ellipse that is the bottom one there, and you see that it records the name of the ellipse, it also records the size, which is the next column along, and then it's got a variable length component that is going to describe the structure, the substructure of that ellipse. And you see that the first element that's referring back to is actually a double. It's got the first two elements that refers back to the double, so that's the first two fields of the double. So this is just describing the structure of the ellipse, and because every compilation unit and then every object is going to have lots and lots of effectively copies of the int data type, we use the linker to keep them unique. So this is just like C++ inline functions. We use similar kinds of techniques to keep them unique at link time. And that's good, of course, because it makes sure that a pointer, if you want to do an exact type test, you want to see, am I looking at an int, exactly an int, then you can do that just as a pointer comparison. So that's sort of nice, fast, primitive. If you want to do something a bit more refined, which is what we do in the instrumentation, which is test, am I pointing at, is this memory, is it an ellipse or is it a double? Then we actually have to do a short search over this structure. So you can see, imagine that we've got a pointer to the start of an ellipse. We're casting that pointer to a pointer to double, which is fine, right? Because the ellipse starts with a double. We should be able to do that. What we're going to do is look up in a table, which I'll show you in a minute. We're going to look up the type of the allocation. That's going to be ellipse. And then we're going to say, OK, at offset 0 into an ellipse, do we have a double? And we search through this. And pretty quickly, we'll find, OK, offset 0, it's got a pointer to the type that lives at offset 0. That's a double. So our search is terminated. And we said, OK, this cast is fine, because at offset 0, we really do have a double. So I mentioned that there's some tables going on in the runtime that we used. Basically, you can give the runtime any pointer, and it will tell you what's allocated at that address. It could be an interior pointer. You could be pointing partway into the allocation, and it will say, oh, you're this many bytes into an allocation of ellipse, or whatever it is. So we use a structure a bit like this. It looks like this to index the malloc heap. There's different structures for indexing the stack and for global variables, but they're all, you can query all of them. It doesn't matter. It doesn't have to be a heap allocation. So here we use the standard trick that a lot of sanitizer-like things use, which is to mmap a big chunk of unreserved virtual address space. So we say we've got an address-keyed lookup that we want to implement, and we're going to reserve a big chunk of virtual address space to sort of model the overall address space of the malloc heap. And then you end up with, when you malloc a chunk, what we're going to do is increment the size a little bit so that we can store some extra metadata inside the chunk, and also thread a linked list in between chunks that are nearby one another. And what we end up with is a hash table-like structure. It's a bit like a hash table in the sense that it's a bunch of linked lists hanging off a linear lookup structure. But unlike a hash table, it preserves locality. So you can take a query on an interior pointer, maybe I'm looking partway into an ellipse, and then we just need to do a short backwards search through the linear structure till we find the chunk in one of these linked lists that actually is has the highest address preceding the query address. So that's how we do a lookup based on arbitrary pointers. We can look up type information for those. And you might be wondering, how much do we pay at runtime for this wonderful checking? So these are some numbers from Spec CPU 2006. And with one glaring exception, you can see that their overhead is mostly pretty low. So the middle column of numbers is the overhead at runtime. And you can see that it's mostly pretty low. So it's mostly sort of 15%, sort of between 5 and, well, 30-something is the sort of the highest sane one. And then we have the annoying case of GCC. This is the GCC benchmark spec benchmark being instrumented. There's a few different factors that make GCC particularly bad. It does a lot of stack allocation. The stack walk is a little bit slower than the other tables. It has the highest allocation rate, the highest cast rate, and it uses a nested allocator that means we have to traverse this tree structure that I showed you a bit more often. So I'm working on some stuff to make that go faster. I think I don't want to commit myself, but I've got it down to about 2x, and I think I can get it a bit better. But that's the kind of spread of numbers that we're looking at for the runtime overhead. OK, a little bit about the status. So Chris worked on the Clang front end. That's in his GitHub. The other stuff is in my GitHub. It does work. It could get a bit faster. There's lots of stuff we want to do with this. Chris mentioned the compiler wrapper. So it's actually a bunch of different processes that implement the compilation stage. We'd like to make that a bit tighter, speed up compilation time a bit more, support more languages. So C++ could easily work, just doesn't at the moment. Yeah, fixing some things in the build system. So there's lots to do. We're very happy to get contributions and happy to take questions. Thanks for listening.
Okay, so for questions, we've got loads of time, so.
Hi there. This seems like a really useful sanitizer to have. In C, there is this notion of effective type, which can change anytime you store to a heap allocated object. Have you considered extending this to track the effective type accurately, so potentially changing the type on every store? And do you have any idea what the additional cost of that would be?
Right. So it's a good question. My observation is that very few C code bases actually use writes to change the effective type. And because instrumenting writes would be massively more expensive than instrumenting just pointer casts and allocations, I've not seriously explored that. Obviously, it could be done. But it's actually, for me, quite interesting that all the things that really change the type are procedurally abstracted. So maybe you would realloc with a different type. Maybe you would memcopy and have that change the type. But because they're procedurally abstracted, we can interpose on them without interposing on any possible write in memory. So I believe this is a sweet spot in that we wouldn't gain a lot in terms of the precision of the analysis wouldn't be usefully improved by trapping writes. But you're right that we do depart from the C standard in that sense. We're basically tightening up a little bit.
Any plans to contribute this? Because I would like it.
Right. I would like it to be contributed. So I'm not a software developer, like I'm a researcher, so I don't have super loads of time, and Chris has also now moved on to other things. So we really want this to get picked up, but we don't have the resources ourselves to make that happen by ourselves, so we can help. But yeah.
So would you be interested in other people?
I would love it, yeah.
Who might want to come up to you and volunteer to contribute?
That would be wonderful.
You mentioned that you check for a type only when there is an explicit cast. What about in the situation that I have two translation units, and in one I define the function with one type argument, and in another I do it accidentally, have another one? Would it detect that one?
Right, so yeah, great question. Currently, no. That's basically a link time check is what you want there. And I have, just about a week ago, I began implementing such a check. I see it as a kind of separate tool because it's really going to be a kind of linker wrapper sort of thing, dumping a bit of extra data at compile time and then checking it at link time. So yeah, it needs to be done. I am working on that. It's kind of separate, but yeah, completely agree.
First of all, thanks for the talk. How much explicit or implicit static analysis can you use? Do you have like a static analysis that you run to actually not annotate stuff because you know it will be safe all the time? Or is the compiler able to actually infer with the optimizations already present in there that some of your calls, some of your warnings can never be triggered so that it removes overhead afterwards? Because you're in a compiler, optimizations are already there.
Great question. At the moment, it's pretty minimal what we do. There's no clever analysis. This is a function, so there's a little bit of caching. There is a function has an inline path, and then which checks a cache, and then its slow path is the out-of-line one that goes into the library. The out-of-line path is marked pure in the sense that GCC and LLVM understand pure, which is not quite pure anyway. So that means potentially it can remove some redundant calls to this slow path. But that's all we've got in that space so far.